Let's talk about the Chinese remainder theorem, and this would be a good application of all the ideal theory that we have built so far. And before going through the proof, I'd strongly recommend that you go back and review the operations with ideals that we studied, like product of ideals. If you have two ideals, I and j in R, then you have something called the sum of the ideals, something called the product. This means all such things, and it's the smallest ideal that contains both I and j. This means all expressions like x1 y1 plus xn yn or xk yk, where the xi's are in from I and the yi's are from j. And that's the smallest ideal that contains all the products of the form xy, where x came from I and y came from j. And you also have an ideal I intersection j. And if you have two ideals I and j, let's see, I plus j contains both. I intersection j is the biggest thing. So I plus j is the smallest ideal that contains both I and j. I intersection j is the biggest ideal that is contained in both of them, and ij in general is something even smaller. You can check that. Okay? So review this carefully before we get started. So for the Chinese remainder theorem, the setup is that R is a commutative ring with identity 1, and we have a bunch of ideals, m1, m2, mn, finitely many ideals. And let's write m for the intersection of these guys. That's another ideal. The key assumption is that if you take any two of these, then they generate the whole ring. That mi plus mj, which is the smallest ideal containing mi and mj, is the whole ring for any pair I and j unequal. Then the intersection of the ideals, which we denoted by m, is also equal to the product. In general, I told you that the product is something smaller than the intersection. Okay, but if they're co-maximal, then the intersection is same as the product, and the main thing is that R mod m is isomorphic to R mod m1 cross R mod m2 cross R mod mn. And if you apply this just to the case of integers, you get something rather interesting. We'll see that, which is actually originally called the Chinese remainder theorem. Okay. So before going to the proof, I'll only prove, I think, when n equals 2. The general proof is written out in the notes, which is somewhat more complicated actually. From n equals 2 to n equals 3, you do need some new ideas. After the n equals 3, you don't need any more new ideas. But I'll just do the case n equals 2. But before that, we need to talk about this condition a little bit. So we need a definition. Again, R is a commutative ring with 1. And let, what do I want to call them? I and j. Just call it m1 and m2. m1, m2 ideals. Say that m1 and m2 are co-maximal, sometimes also called co-prime, if m1 plus m2 is R. So example, Can you think of what are the comaximal ideals in Z? I claim like 8Z and 15Z are comaximal. Because if you take all multiples of 8 and add to it all multiples of 15, what is that? That's the whole ring. And why? It's because these two numbers are relatively prime. So you can write 1 as some multiple of, how do I go about this? Some multiple of 8 plus some multiple of 15. So this ideal 8Z plus 15Z, my M1 plus M2, contains 1. And if it contains 1, it contains all the numbers, because once it contains 1, it's going to contain all the multiples of 1, which is all the numbers. Okay, so saying that two ideals are comaximal, so two ideals so this is what I'm saying. Check this. MZ and NZ are comaximal. Why do I call them MZ and NZ? Let's call them M1Z and M2Z. Are comaximal if and only if the numbers M1 and M2 are coprime. So the GCD is 1. Okay, so that's the comaximality condition. That's how you understand it. Let's verify this little lemma. That if M1, M2 are comaximal ideals in R is still commutative ring with 1. Then the product is same as the intersection. By the way, if they're not comaximal, you can see that the product and the intersection are sometimes different. I'd leave you to find an example like that. For example, maybe I can give you. So look at the ideal 2Z and the ideal, well, 2Z again, why not? What's the intersection? The intersection is 2Z again. But what's the product? The product is the ideal generated by pairs of the products of the form xy, where x came from M1 and y came from M2. So x is a multiple of 2 and y is a multiple of 2. So the product is going to be a multiple of 4. And if you add a bunch of products of 4, add a bunch of multiples of 4, then you again get a multiple of 4. So the product in this case is multiples of 4, which is strictly smaller than the set of multiples of 2. Okay. So in general, one is contained in the other. But if you have comaximal ideals, then the intersection and the product are the same. Why? Well, this inclusion is always there. This I'll leave you to verify. Verify that the product is always in the intersection. The product is always a subset of both M1 and M2. That's what you need to check. The main point is the other one. So you take, and that's what uses that they're comaximal. Since M1 plus M2 is the whole ring, the element 1, the 1 of the ring, belongs to M1 plus M2. So I can write 1 equal to something from M1 plus something from M2. Because that's what M1 plus M2 means. It's up, up here. M1 is from M1 and little m2 is from m2. Now take A in the intersection of m1 and m2. Then A is same as A times 1, which is same as A times m1 plus m2, which is same as am1 plus am2. Now notice that am1 is in m1, m2. Why? Since A is in m2 and m1 is in m1. Because A is in both, so it's in m2 in particular. So this product is in the product. And of course there is no left and right, we are in a commutative ring. Okay, and also am2 is in m1, m2. Since A is in m1, again it's in the intersection, so it's in both, and m2 is in m2. So both these guys is a product of a thing from m1 and a thing from m2, so they're both in the product, and their sum is also in the product. So A, which is am1 plus am2, both these guys are in m1, m2, so the sum is also in m1, m2. Okay, so if something is in the intersection, then it's in the product. Okay, we'll continue. And I'll indicate the proof of the Chinese remainder theorem for two ideals for the n equals 2 case in the next one.